voltaic or galvanic cells are electrochemical cells that are favorable. We classify it as voltaic if these three things are true. It's thermodynamically favorable, which means the overall reaction would have a negative delta G and a K greater than 1. The current flows without needing an outside source, and the voltage for the reaction, which we'll talk about, is positive. So just by looking at a picture, if we have any of this information, we can know that it's voltaic. A voltmeter with a positive voltage is one side. A electrolytic cell would be plugged in maybe to the wall, or it would say electricity source. So we have no voltage source. The current is flowing on its own. We can also, and we will, look at calculating where the voltage comes from and why something's oxidized or reduced. In this one right here, we have a zinc anode and a copper cathode. They're the electrodes for the cell, and those metals eventually will get into an equilibrium with the zinc metal and zinc ions in solution, or copper metal and copper ions in solution. Both of them, through a reduction process, would lose 2 electrons. But the equilibrium position or the likelihood that they will be reduced isn't the same. Zinc is much more likely to ionize or oxidize, lose electrons. I misspoke when I said they were both reduced. These are both oxidations. It loses more easily than copper. We can think of that in terms of the reduction, the reduction potentials that we'll see, the activity series. Sometimes when we look at single replacements to decide what is most reactive, or the stability of the ions themselves. So the fact that zinc is more likely to lose an electron than copper determines that zinc is going to be the thing that will be oxidized, and therefore copper will be reduced. So when we look at this, we don't think of it as an equilibrium, because if it were an equilibrium, then we would not have an overall loss or gain of electrons. Eventually, we will get to equilibrium, but we're going to start off with the more likely to lose or ionize as the oxidation, the zinc, and the copper will be reduced. The zinc is the anode, the copper is the cathode. And when we put this all together, zinc turns into zinc ion and copper ion turns into copper metal. If we put these in the same container, we would see changes in terms of what's forming or what's dissolving. But for an electrochemical cell, they're going to be separated. They're separated by a wire that electrons can flow through and a salt bridge that ions can flow through. And we see those here and here, and we'll discuss each of those. The electrons that the zinc loses, these electrons right here, are the electrons that copper needs to gain. As it loses those electrons, the zinc metal atoms actually ionize or oxidize into zinc and dissolve away. We come up to this picture here, that big piece of zinc we see is dissolving or breaking away, and our zinc is actually going to get smaller through the process. Copper, on the other hand, the solution of copper that we have gains 2 electrons and turns into a copper metal. The copper gets bigger. So the electrons are gained by the copper 2 ions and turn those into atoms. So we can't see the electrons themselves moving, but there are some important signs of what's going on. So as the zinc metal oxidizes, it dissolves. So that anode is going to get smaller and smaller and smaller. It will decrease in mass as it dissolves away. As that oxidizes, it creates cations, and there's a solution of zinc ions right there. And depending what we have, as we get a higher concentration of ions, we know from Beer's law, the solution may become more darkly colored. That's not the case with zinc, but it is with many things. And also, as that zinc oxidizes, loses its electrons, and turns into cations, that throws off the charge within the solution. The salt bridge is a bridge between them that contains a salt, very cleverly named. It's described below. So to account for the fact that there's extra cations in solution, the anions from the salt bridge flow into the anode solution. So anions flow towards the anode. When we look at the other side there, the copper cations used to be dissolving around. They are turning into solid copper atoms, and it's increasing in mass. We said before, fat cat meant the electrons went from anion to from anode to cathode, but that also reminds us that the cathode gets fatter. So as they reduce, our ion solution goes down. That means any color associated with that may decrease. Copper solutions do have a color, so that would actually fade in color as the reaction proceeds. As they gain those electrons, the positive charge goes away. So what has to happen is we have to account or compensate for loss of positive charge. So the positive cations in the salt bridge flow towards the solution of the cathode. Some things we want to remember here is that there is a change in mass. The anode gets lighter, the cathode gets heavier, and that's because we are taking solid and dissolving it into ions, or ions and turning them into solid. It's not the electrons themselves, which are almost massless. Within the salt bridge, it is the ions from the salt bridge that flow through the bridge. Electrons can't go through the salt bridge, and the ions from the solution don't significantly do much with the salt bridge. It is the cation towards the cathode, the anion towards the anode. Some of these reactions, and we'll look at a lot of them together, will produce a gas. So bubbling at the cathode or anode at an electrode is often a sign or an indication of what is reacting in that reaction. So then the last thing for this video is just kind of stating a little bit more about the salt bridge. The salt bridge is a porous barrier, or it is something that is kind of stuffed full of either an ionic solid or a very high concentration solution of that ionic salt. It helps from building up a positive charge or a negative charge on either side because the ions in there can flow into the solutions. But when they do that, we want a strong electrolyte, but we want a non-reactive electrolyte. NaCl works in this example because sodium doesn't react with nitrate or with copper or with zinc, and chloride doesn't react with zinc, nitrate, or copper. Potassium nitrate's even more common as the salt for the salt bridge because potassium doesn't react with almost anything to precipitate, and neither does nitrate. But the salt bridge completes that circuit and allows the flow of charge to continue.